Hey guys, it's Professor Gillian, and today we're going to be discussing gas exchange. We're going to be looking at different gases in the respiratory system and examining why they move the direction they move. So, for example, in the lungs, the oxygen will enter into the bloodstream, but in the tissues, the oxygen will leave the bloodstream and enter into the systemic tissues. On the other hand, carbon dioxide in the lungs will leave the bloodstream, but in the tissues, carbon dioxide will enter the bloodstream. So the question is, how does this gas know which direction to go? Why does it enter the bloodstream in one place and leave the bloodstream in another? Well, the answer lies with partial pressures. So both of these gases will follow their partial pressure. Oxygen will move from higher oxygen partial pressure to lower oxygen partial pressure. Also, carbon dioxide will move from higher partial pressure to lower partial pressure. So let's look at what these partial pressures are. So take a guess. What percentage of the air you breathe do you think is oxygen? Well, if you answered 21%, you're right. Some of you may have known the answer to that question. Others may have guessed. And a lot of times when students guess, they guess that it's a little bit higher of a percentage than 21%. But the air that we breathe contains approximately 21% oxygen. So if the total air pressure of the air you're breathing is 760 millimeters of mercury, then how much of that pressure is due to the oxygen in the air? So to calculate that, you would multiply that 760 millimeters of mercury times the 21% that's oxygen, and you get 159 millimeters of mercury. So that 159 millimeters of mercury is the partial pressure of oxygen. So here's a little table that shows you the partial pressure of the air you breathe in, and there's oxygen at 159 millimeters of mercury. The water is 0.5%, so that gives it 3.7 millimeters of mercury, and the CO2 is 0.04%, so only 0.3 millimeters of mercury for the air that you breathe. Now, when you breathe it in, the air in your lungs has a little bit of a different composition. So if you look at this column here, the alveolar air, you'll see that the oxygen is lower, the water pressure is higher, and the CO2 is also quite a bit higher in the alveolar air than in the atmospheric air. So why is this? Why is the water vapor pressure higher and the CO2 higher and the oxygen lower? There's three reasons for that. The first is that the air is humidified by the mucous membranes as we breathe it in. So as it passes through the nasal cavity, there's quite a bit of moisture that's added, and that will increase the pH2O. Also, the air in the lungs is not all breathed out when you exhale. So there is residual air left in the lungs, and the residual air in the lungs is higher in CO2 and lower in oxygen. And so the oxygen you breathe in gets diluted out, and also the air you breathe in has lower carbon dioxide, but there's quite a bit of carbon dioxide in that residual air left in the lungs. The other factor to consider here is that the alveolar air is constantly exchanging gases with the blood that's delivered to it. So because of that, you've got this sort of constant flow of blood to the lungs that's deoxygenated, so lower levels of oxygen, and a lot higher levels of CO2 because it's carrying the CO2 from the systemic tissues to the lungs. So now let's specifically look at gas exchange that happens in the lungs. So that's the alveolar gas exchange. And in this alveolar gas exchange, we learned that the gases move across the respiratory membrane. The respiratory membrane is what separates the blood and the air in the lungs. And so typically it's just the endothelial cell of the capillary plus the simple squamous cell of the lungs and a shared basement membrane. So a pretty thin little respiratory membrane for the gases to diffuse across. There's also a little bit of water covering the alveolus, and that's another part of this gas exchange, the gas has to go through the film of water as well. So if you look at the direction that these gases move, they will move down their concentration gradient. And to look at their partial pressure, or you can examine their partial pressures to determine which direction is down the gradient and which direction these gases will move. So in the lungs, the partial pressures dictate that the carbon dioxide will be unloaded, so move from the bloodstream to the air and breathed out, and that the oxygen will be loaded into the bloodstream, move from the air and into the capillaries. All right, so let's take a closer look at oxygen. So here you can see that when you breathe in, the air you breathe in has a partial pressure of oxygen that's 159 millimeters of mercury. And we just discussed how it's a little different in the lungs because there's residual air left in there. And so the partial pressure of oxygen in the lungs, in the alveoli, is 104 millimeters of mercury. It actually, the blood leaving the lungs actually combines with a little bit of systemic blood from the bronchial veins. And so it's, when it's transported, it's PO2 of 95 millimeters of mercury. And then it hits the tissue fluid. And when it hits the tissue fluid, it encounters an environment with a PO2, a partial pressure of oxygen, of 40 millimeters of mercury. And so oxygen will move along its partial pressure gradient from higher to lower partial pressure. So it'll move from the bloodstream, with a partial pressure of 95 millimeters of mercury, and into the tissue with a partial pressure of 40 millimeters of mercury. That gas is then transported back to the heart, and it's going to be pumped back to the lungs, and the air you breathe out has a partial pressure of oxygen of 116 millimeters of mercury. Now I would challenge you to do the same thing, go through this entire chart, and this time follow the path of the carbon dioxide. Determine which direction the carbon dioxide will move based on its partial pressures.